Good morning, everyone. We will wait until it is 11:05, and then those who come late will be late. All right? Tell your husband to come quick.
Okay. His parking car.
Oh, and it is raining. Oh, maybe a little bit late. It's okay. Quiz 4. I'm talking about quiz 4. So I assign A as 1, 2, 3, 9, 4, 2, integer, okay? And B equal to STRA. This means I convert A, be careful of my camera, okay? Don't hit the tripod. So I change from integer type to string type. So B is string of that. C is list of string. List B, so it breaks B into several digits in order. Okay, and then I have sum equal to 0, 1 I in C. So float, or you can use in I. Let me delete this two line. So sum equal to sum plus float I. So this means I change from character to number first, right? And then I add together. This is how we do summation. To do summation, we do sum equal to 0 and have for loop. Okay. Automatic function, we will use that with numpy. I think you can use dot sum with numpy already. I'll find out tell you later, okay? So with this, you can actually do quiz 4 already. Good?
So what's that? For the quiz?
Quiz 4, can you do it? You didn't prepare for quiz 4?
But not today, right? Wednesday.
It can be today.
Oh no.
I just didn't print it out. So you should be fine. So homework is first question, that maybe is a little bit mistake in the homework. 10 to the power of 8 plus 3 may not be there.
Yeah.
But if you can get the rest, it's okay. Let's continue what we have. Previously we finished basic programming. No, I don't do that. We are not talking about this, okay? We will do. Oh, first thing, syllabus. You have 14 days to turn in your missing report for missing class, and you state your university skills, and you give me the report. Done. Okay, the report should be good. If your report is bad, you get less than 10. That's class missing.
Less than 5.
Oh, less than 5, not less than 10. All right. And if you notice, I have bracket and parentheses. Parentheses mean including A but excluding B. So if you miss even once or come to class late, what is this now? What time is it?
I don't have one.
Oh, this is not late yet.
Yeah.
This is not late yet. No, it's not late yet. You still have to second. Okay. So if you ever miss even once, you are not eligible to get A+. Okay. So today we will go over root finding algorithm, and we may not be done. So according to the syllabus, you may think that we are a little bit slow. Okay. But hopefully you know all the basic, and when you know all the code, then we can just go faster later. Okay. And as promised, 4th of October we will have exam 1. Next Monday, I have to check the schedule with Lindsay, Charlotte, to see if it is this room or the room in 110, and I will tell you. But this coming Thursday is this room. So, have anyone, did you see the example of the exam?
Oh, yes.
You did? What about you, Hasid?
Yeah.
You did? You see the example of the...
I was like doing homework all the time. So.
Okay, alright. But the example of the homework is available in the blackboard. And this week you don't have homework to do. And it is your choice to prepare for the exam or not. But the exam will come, okay? Alright, today we will try to finish the root finding operation if we can. Maybe we may not be able to, okay? And whatever we finish within this Wednesday, it can be in the exam, okay? Alright, root finding operation. Last time we talked about this. Fixed point iteration. Sometimes it converge, sometimes it diverge. Okay, and we talk about this example that, hey, for this case, it diverge. Alright, so fixed point iteration is when you type x equal to something, and you keep putting value into the right hand side, and take the output from the right hand side as a new x, and keep putting it in the right hand side. Alright, so this is and we have the case where it doesn't convert, do we? Sometimes it do this. So this equation is x equal to 3 exponential of minus x minus 1. And it's just jumping around. It doesn't converge to any value, which is not good. Okay? And I showed you last time that for x equal to 3, xp minus x minus 1, it's like we keeping moving outward. We start from one point, okay, calculate the right hand side, and take that right hand side value as a new x value, and keep doing that. And for this case, we are moving away and we don't converge. Okay. What do we do? Rearrange this equation x equal to 3 exp of minus x minus 1 into another form. Okay. Instead of this x in the form of the right hand side, we try to make this x in another form. So for this x, what we do? We have x plus 1 divided by 3. Everything take natural log, okay, and multiply by minus 1. Just like rearrange the equation, okay? And then it converts. Wow. So I want to show you what is the calculation part. So when I start from this point, I calculate the right hand side and take the right hand side as a new x value, and calculate the right hand side again and take the right hand side as the x value, and keep doing that. It converges to the cross point. Okay. So whether it's converged or not, it depends on how they cross each other. Okay. So left hand side equation is x, right? It's like y equal to x, so slope is 1. So if right hand side equation has a slope of minus 1, we get infinite loop. Let's take a look. Okay, this case, let's say, okay. By the way, we try to do this because when we write x equal to some function, you can have this line, 45-degree line, cross with another line, right? And whether it's a curve or anything, but when you zoom closely, when you zoom close enough, we can assume that it's linear, okay? So even though the blue line is a curve, right? Blue line is a curve, but very close, you can say, hey, it's linear, okay? Very close to the cross point. So if the cross is like that, so very close, it is like what? Slope of right hand side equation is equal to -1. So when you start from one value, you calculate right hand side, you take that value as a new x value, and you keep doing that. So you keep moving around, don't go anywhere, doesn't converge. Okay? What if the slope is less than -1, like -2 or -3 or -4? I mean steeper, kind of steeper. When you go from that side down, and if the slope is less than -1, like a little bit more steeper, dropping steeper, it diverges, doesn't converge, according to this picture. Okay, you start from this point, you calculate right hand side equation, you take that right hand side equation as a new value, keep doing that, it diverges. So if the slope is more than -1 or like less steep, gradually decrease, when you keep moving, it go to the cross point. Okay, so basically you need to know that fixed point iteration doesn't always converge. Sometimes it's just moving around and doesn't go anywhere. Okay, sometimes it diverges. Okay, so for the case where it's moving around, see, your new answer will be the fluctuation between these two, right? One and another one, but you don't get the right answer. Okay. So if you have it diverge, you kind of inverse your equation, then it will be converge. Okay. But if it's moving around a fixed point, cannot do anything. Chain operator. We will see how it works later. Next, let's talk about bisection method. Who have never used it before? Hasib?
Yeah.
Have you used it before? Bisection method. Why didn't you not raise your hand? Okay, you raise your hand. Who else have never used bisection? Okay. You may consider it as like divide and conquer. You separate the domain into two halves, and you see the left side, do we have answer? And the right side, do we have answer? Where's the answer? If the answer is on the left, we focus more to the left side, and then we divide it again. Okay, we keep doing this. So we divide the domain into half and check each section for the answer. If the answer is in the left portion, define new search domain to be the left portion. If the answer is in the right portion, define the new search domain to be the right portion. Once you get the new search domain, we divide it again and keep doing that, okay, until the domain is smaller than a certain epsilon, a small number. This means your answer will be at least output plus minus epsilon. Okay. All right. How do we find whether the answer is on the left side or the answer is on the right side? So first thing we define, what do we try to solve? We try to solve fx equal to 0. Okay. We try to solve fx equal to 0. So we define left side and right side, L and R. Okay. Then we find the middle point, L plus R divided by 2. That is the middle point, right? Next step, we find the function value, FL, FR, and FM, the function value. So the function value, okay, we will go to the example later. So once we find the function value, we compare the function value. So fx equal to 0, this means if there's a change from positive to negative or negative to positive, that means in that range you have answer, right? Make sense to you? So f of left boundary is negative value. F of plus number equal to positive value. This means the answer is within those two. So if f at any point is 0, this means we are done, right? If we very lucky, we put something in and f of that is 0, then we are done. We don't have to do anymore because we find x where fx equal to 0. But if not, we compare FL, FR, and FM to find if the answer should be between L and M or M and R. Once we know where's the answer, then we update the search domain, okay, accordingly. Okay, let's see this equation, Colebrook-White. What is this equation for? Tell me to pay.
It's for friction factor.
Oh, it's for friction factor. Okay. It's for friction factor. For Raynon, but this is implicit form, right? We cannot write f equal to something. Okay, so left hand side, in order to know left hand side, we need to know that part. We can use fixed point iteration to solve this. Okay, and you may have to do that in the exam. Make sure that you prepare for that, but it may not be in the exam either. Okay, so to solve for fixed point iteration, we put the value of f into the right hand side equation, keep doing this, and then we're done. Iterate it. Okay, for bisection method, we rearrange such that if the correct value, actually this is x and this should be x and that should be x too, okay? If we find the right x, then equation equal to 0. So basically what I did is I used left hand side minus right hand side. Okay. So what I do is I give you the pseudocode. First step of doing the calculation, I define the function. Function is lambda of something, something, something. So define the function. After I define the function, I define what is the left boundary and the right boundary. Okay, L is small value 1 e minus 9 r equal to 1. I think the answer should be between 0 and 1, so I put that. So for 1 to max iteration, I calculate the middle point between r and L. Calculate function value at L, function value at R, and function value at M. Okay? Alright, now, if the sign can be minus 1 and 1, or maybe 0, okay? But typically it's minus 1 and 1. So if the sign, you have the sign multiply each other, and the sign equal to minus 1, this means the answer is in that range. Okay. So first I multiply FL and FM, sign of each. Okay. And if it is less than minus 1 or equal to minus 1, this means we update the domain by moving point R to point M, because the answer is between L and M. L is left, M is the middle, R is right. So if the answer is between left and the middle, so we move the point on the right, point R, to the middle. So this means we shrink the domain. Okay. So if the opposite happens, we move L to M. Okay. And then we finish whenever we converge. Let's take a look on, that's done. And we will show more in the Akata notebook, okay? And you will see the full code. Right now you just know that we divide it in half and we compare the function value. If there's a change in sign, then we are done. Good? Any of you that don't understand? Daniel, what is the first step for bisection method?
You will define your left and right boundary.
What's next?
Then you find the middle boundary. Then you evaluate your function at those different boundaries. Probably check.
Pardon me, I don't get it clear. After you define L, R, and M, what do we do next?
Then you evaluate your functions at each of those points.
Calculate the function value at each of those points.
Yeah.
And what's next?
Then continue
say that you don't know. Yes.
Why did we define the left hand side equal to 0 rather than just be defining it like 1 squared minus 9? What's the point of that?
L
Yeah.
can be very low number, for example, minus 10,000. But this time we define L very close to 0, but not negative number or not 0, because when you put in your friction factor function, you don't want to have negative in the square root. For this question, the domain of the answer is something greater than 0. 0 doesn't work, right? 1 over square root of 0 is infinity, so it doesn't work. 1 square root minus 10 doesn't work. Okay? So because of, for this case, right? You see more of the code, but right now, okay, Daniel, how do we find if the answer is between point L and point M or not?
How to find the answer is between.
How do we know if the answer is between L and M?
We'll have a change in sign
Change in sign of what?
of value of the function.
Value of the function. Okay, alright, you got it. Alright, let's do Newton method. Okay. Newton method is, it's like first you start at one point. You draw it up or down until it cross with your function that you want to calculate the answer. So from that point, you find the slope. Once you find the slope, you draw it. You follow the slope until you cross with the x-axis. Okay, you follow the slope until you cross with the x-axis. Once you cross with the x-axis, that's your new starting point. From your new starting point, you find the function value. So you get that, right? Function value. Then we calculate the slope. After the slope, we extend that line until it crosses with the x-axis. And then we keep doing this until we find the point where fx equal to 0. Easy enough? Yes? Oh. Tope? Easy, right?
Makes sense?
Okay, how do we follow the slope? The definition of the slope, f prime x. Slope is delta y divided by delta x. Okay, but delta y we know that. Look at this line. Delta y will be that point minus 0, because we start from 0, right? We start from y equal to 0. So slope is delta y divided by delta x. So delta y is that point. That point is f of xn. If we start at xn and we try to get xn plus 1. So delta y is fxn. And delta x is the distance. So that distance is xn minus xn plus 1.
Professor, can you start again? I'm not getting it.
The definition of the slope. I mean, what is your definition of slope?
It's difference, this is delta y upon delta x. Is
Okay,
all-
okay. When you look at that triangle,
Yeah.
what is your delta x?
Delta x, it should be, it's the same here.
What is that? Read it if it is the same.
It's on the same line, so it's, delta x is 0 here.
Oh, no. I mean, this triangle, you see,
Oh,
That
in the
triangle?
It's
Okay, I see it.
This
It's
triangle-
215 minus 1.8, 1.6 I guess.
Excuse me, sir.
so
Yeah, this is it.
that is delta x.
Okay.
Delta x is xn minus xn minus 1.
Okay.
So, but you should be xn plus 1 minus xn or xn minus xn minus 1.
This depends on the definition of where's xn and where's xn plus 1, okay? So I define your start point as xn. And your next point of iteration is xn plus 1. So delta x for that triangle is xn plus 1 minus xn. That's delta x
Yeah, I know, so it's
by definition.
a little bit confusing.
It's not a little bit confused, that's by
Actually,
definition.
the way I think is because if you're converging to the right value of x, so that's why we're calling it plus.
This time we call xn to be the current iteration and xn plus 1 is the next iteration. So the idea here is you try to go from this point to that point to that point until you reach the cross point. See what I'm saying? So next iteration is n plus 1. So the delta x for that triangle is xn plus 1 or xn, which is this, minus xn plus 1. That is delta x. Delta y is that minus that. Right? If you look at this blue line, the slope of blue line is positive or negative? I mean,
What?
the slope of blue line, this blue curve,
Yeah.
at that point, is it positive or negative?
It's negative.
It's going up.
Yeah.
Going up is
No, I'm talking about the blue line.
the blue curve.
Okay.
The slope is
It's positive.
it's positive, right? And if you do it my way, are you going to get positive value? What do you think? Fxn is positive, right?
Yeah.
And that delta x is also positive.
Okay.
So if you do it my way, you get a positive value. You like it? Now maybe you like it better. Alright, we rearrange a little bit, we get this formula. Very powerful. Xn plus 1 equal to xn minus f xn divided by f prime xn. F prime xn is the slope at xn. Okay? So this means you use slope at the current iteration to guess the next point. Okay? Got it? That is the formula that is it given in the exam sheet? No. Do you memorize it? You don't need to memorize it if you understand the definition. Oh, maybe, I think it may be given. This thing may be given, I don't know. I'll check. So basically, you go from the definition of the slope, delta y over delta x. You rearrange it a little bit and then you get xn plus 1 equal to xn minus function value divided by slope. And if you keep doing that, eventually you will approach the answer. And this way of doing it is faster than the bisection method or fixed point iteration. 10 times faster. Okay? Sometimes it doesn't convert. For example, this case. We know that fx equal to 0, x that make fx equal to 0 is somewhere over there. Okay? But if we start from here, we start from 1.5, we draw up, okay, we reach the line, we get the slope, we follow the slope to find the next one. We end up over there, right? We go up again, we reach that point, we follow the slope, we get that point. Here's come the problem. We go up again, we get that point, we follow the slope, we move back to the same point. And if we keep iterating, we keep doing that thing like butterfly shape. We keep moving back and forth. You didn't reach the answer. Not what? What do we do? Cannot do anything. Or we can do something.
Change the domain.
What? Nan, what is your suggestion?
Change the domain.
Change what? Domain?
Yeah.
What is domain? Change what?
Change x to
Or you try to
the condition at the beginning we should change.
initial condition. Instead of starting from 1.5, we start from 2. Look at this. If you start from 2, you go up, follow the slope, go up again, follow the slope, go up again, follow the slope, but this time your slope make you go to the negative side. And then when you go up, follow the slope. Now you have to go down to reach the line, right? You follow the slope, and then you will reach the answer. Okay? If the initial guess is close to the actual answer, you have a better chance to get the result. Okay?
Excuse me, sir. Sir, are we having problems because we got to a point where the slope was negative? Because when we
Slope is negative, and then what? My formula is going to be invalid?
no, I mean the point where the iteration.
Okay. Look at this formula. I'm asking you, from the way that it is derived, that is work if you flip the curve. Instead of curve going up like this, you do that. Does it work?
No, sir, I don't have a problem with this one.
You didn't answer my question. My question is, instead of the graph going up like that, I have the graph that going down like this. Does it work?
No.
It works. So this formula works for any case. If your curve go up and cross zero, and your curve moving down and cross zero, either case, you end up with the same derivation. It works anyway.
Okay, but I mean this is not my question.
So when we are at that point, what do? We follow the slope, do we? We follow the slope until it crosses with x-axis. And it crosses over here. When we are over there, we find function value. F of minus 2 something is that. Right? How do we go from the value on the axis to be the value on the line? You have to find that value, right? The function value. So this time the function value is just below 0. Once we find the function value, what do? We follow the slope until it reaches x-axis. Not clear? Clear enough? You like this one, Daniel? Does it answer your question?
No.
What's your question?
My question is that, I mean, for when we change the initial condition, we see that the iteration skips the part of the graph where we have a negative slope. And the last one, it actually iterated through that negative slope region. So I'm trying to ask if the fact that we encounter negative region in the slope is responsible for why our algorithm couldn't converge the iteration. Go back to the next graph, let me show you. Yeah. If, between 0.5 and 0, there's a change in slope in this graph. So it went from 1.5 to 1 was positive, the other one became negative, and then it went back.
It doesn't reach this part where slope is 0, you see. It is a little bit before the minimum. So the slope is still positive. That's how we get there. And I didn't just draw this, okay, this is according to the calculation we saw. Sometimes if you ever go into this region, the slope is negative and then you're moving back. And then you may have that problem.
Yeah, that's what I'm asking, yeah. Okay.
That is true.
Okay.
So it is not for sure that your Newton method will work. Sometimes it may not work when you select anything above 1. You may have to select something over here. It's not always that it converges. Bisection is always converge, provided that your initial guess of the range contains the answer. Okay?
But given most of the time, given enough iteration times, you will convert most of the time.
For Newton method,
Yeah.
it depends on how you iterate.
But
If you iterate without changing the initial condition, look at this one. If you slide over there,
this is really special. Most of the time.
this is very special.
Yeah. Really.
This is very special. Most of the time it's not like this. I agree. But when this kind of thing happen, you have to be aware that maybe all your code is good, but the reason that you don't get it because the algorithm itself doesn't allow you to get it. It can be like that too. So when you finish your code, you don't get the result. How do you know that your code is right or not? You compare with the easy case first, okay, and then you can try for more complicated one. And the point of this presentation is to show you sometimes it may not converge. Just need to know that, okay? Sometimes you have infinity loop, and the value just fluctuate between 2 points, but it doesn't mean that the real answer is within those 2 points, okay? All right, how do we get the slope? Any idea? Your way? How do we get the slope? In Newton method, we need the slope, right? F prime. How do you get the slope?
So, difference between the y value over the difference between the x value. So delta y over delta.
For you, you should tell me that, okay, we use finite difference. Because you studied that already. For other people, it's okay. So we can use finite difference method. Okay, x plus 0.5 epsilon minus x minus f of x minus 0.5 epsilon divided by epsilon. So we can use finite difference approach to estimate the slope. Okay, if you do it like this, it is central scheme. The point where x plus a little bit of something minus the point where x minus a little bit of something divided by epsilon, okay, total gap. Okay? So this means the function f, it has to be available. Or you can use the analytical solution for f, but if it is too difficult to get analytical solution, you can use this. Okay? So this way we don't have to directly take the derivative. Alright, there's something to be careful. When you use computer, double precision, you can have 15 to 16 significant digits. Okay? And otherwise you have to do like maybe long double. Long double can have more than 15 digits. Another thing is, epsilon for stopping calculation criteria cannot be smaller than this kind of epsilon. Okay? If your epsilon for stopping the calculation is less than this, you get a problem. Because whenever you approximate the slope, you never get as accurate as the epsilon that you use to stop the calculation. Okay? So this epsilon for slope should be smallest in your numerical scheme. The epsilon for stopping the calculation should be a little bit larger than that. Okay? Alright, so let's give you summary. Fixed point iteration has linear convergence, does not always converge. Okay? Bisection method is linear convergence slow, okay, but it's always converge. Newton-Raphson, quadratic, okay, but it's not always converge. So the requirement for bisection method, your function has to be continuous, okay. Non-differentiable is okay, but for Newton-Raphson, it has to be both continuous and differentiable. Where's Landry? He gets stuck in the rain or something?
Oh, I think he's running. I don't think he wants to continue.
He's gone.
I think so.
Alright. Ami, can you tell me about, just a little bit more. Ami, can you tell me about non-differentiable case? Non-differentiable but continuous, how does it look like?
Absolute value of x.
No answer from you? Okay, look at this orange line. This orange line, that's continuous, right? Because you have the same, it's continuous everywhere. But at that point, the slope from the left and slope from the right, they are not the same. So at that point, it's not differentiable. And actually, this whole line, the slope is infinity. It's not differentiable at that point. So if you have any abrupt bending like that, that is mean it's not differentiable. Okay. For the case where something like this happens, bisection may have a hard time to converge. Okay. But if you have just like this line go up and down, bisection work. Newton-Raphson doesn't work. So for Newton-Raphson, it has to be smooth. So it has to be both continuous and differentiable. And we will learn the rest in the iPad notebook. Please restart.